So the second part, we're now talking about logistic functions. So let's go to page 258. 258. So we briefly talked about logistic functions in the P chapters when you initially started. Okay, a logistic function is a function that really, if you look at, there's a blue box there. If you read it, it says f of x is going to be equal to c1 plus a times b to the minus x, or just say b to the x, I guess, b to the x, or 1 plus, it also says a e to the negative kx, okay? All right, so this is what a logistic function looks like. Okay, usually this is more prevalent. You're going to see this more often than that one. Okay, but anyway, the function is going to look like this. The function is going to look like this. This is your x, and you're going to have a horizontal asymptote. So you're going to have a horizontal asymptote this way, and you have a horizontal asymptote that way. So the horizontal asymptote going that way is going to be 0, obviously. So try to get to 0, but it never will. And up here, you're going to have a different horizontal asymptote up here. Okay. The horizontal asymptote up here is basically C. This is C. So, and you can take a look at it if you see this, right? If x goes big here, what's going to happen? If x goes big, this guy becomes 0. So x goes big, x becomes large and large and large, right? This becomes 0, you get C over 1, so that's where you get the C. Okay, and the reason why it's called C is because it's also called the carrying capacity. Carrying capacity. Okay, and we will talk about this not only here, and you'll also talk about this later on in calculus too. Okay, so this is the carrying capacity, it's a C. Okay, all right. So this point here is what? So if I had this guy, this point where we would be what? Where x equal to 0, right? When x equal to 0, this guy here becomes 1, becomes e to the 0 power, which is 1. So this is going to be c over 1 plus a. That would be your your y-intercept there, right? Because y-intercept happens when x equal to 0. Okay. So let's go ahead and see if we can do example number 6. Example number 6. Example number 6, where are we on the wrong one? Okay, graph the function, find the y-intercept, horizontal asymptote. So A, I'm going to have f of x is equal to 8 over 1 plus 3 times 0.7 to the x. Okay, so it's going to be a logistic function that's going to look like this. Okay, the carrying capacity is 8, so it's going to be 8 up here, right? Because it's a number up here, 8. The y-intercept is going to be when x equal to 0. Zero power. This guy is 1. So my answer is going to be 2. Okay, that's it. So now let's see if we can do B. That was A. And in B, we're going to have g of x is equal to 20 over 1 plus 2 e to the negative 3x. Again, it's going to be logistic function here. when x goes all the way out here, well, okay, this is the carrying capacity is going to be 20, right? Carrying capacity is going to be 20, okay, because this is what's on top here. Let's go ahead and do the y-intercept. Y-intercept happens when x equal to 0. E to the 0 power becomes 1. 20 over 1 plus 2 is 3. So this is going to be 20 over 3. Okay. That's that. It's really not that complicated. Okay, let's flip the page and now let's talk about population models. In your previous career in math, whenever we talked about populations, you usually did an exponential regression and said that the population is going to follow an exponential pattern. Okay, in other words, it's going to look like this if it's growing. If it's dying, it's going to go this way. Okay, all right. So either one of them, right? So let's do this. We can do example number 7. Example number 7, the population. So I'm using the data in 3.5 where we had the year 2000, 2007. We had 898, 739, 939, 899, 759. Okay, so using this data and using the data and assuming the growth is exponential, when will the population of San Jose surpass 1 million? Okay, so this is going to be the original value. We'll call this time 0, right? So the time 0, so the population is going to look like 898. This is going to be the initial value. And then it's going to be something b to the x, right? We need to figure out what b is, but what we do know is that when x equal to 7 years later, I'm going to get this. So I'm going to get 939,899 is equal to 898,759 b to the 7th. So therefore, b to the 7th is going to be 939,899 divided by 898,759. Essentially, I just divided this guy underneath here, and all I'm going to have left is that. So b is the 7th root of this. All right, so there's your answer right there. Okay. If you do that, you're going to get a 1.0064. Okay, so your final answer is going to be what? Your final, not your final answer, but your final modeling is going to look like this. 898,759 times 1.0064 to the x. Okay, and the question is, when is this going to be 1 million? So you would set this to 1 million. You would solve for x. So the way you would do this with your current knowledge is you would just have to graph it and find out where it meets 1 million. Okay. Shortly, in about a couple, 2 or 3 sections later, we should be able to figure this out algebraically, but we'll do that later. Okay. Right. So that's example 7. Okay. So what's the problem? Well, not say the problem. So let's kind of look at this. Okay, you can look at population in short spans and say it is an exponential function. Okay, however, if you look at an exponential function, there is no end. There is no end to how it grows, okay, which is essentially, this is unrealistic, right? because Salem's population is never going to become 140 million people. It's just not going to happen. Okay, so this is really not a realistic model. Okay, so the more realistic model is that a model which includes a limit to the growth, right? In other words, the logistic function is a more realistic way to model population growth. Okay, all right. So let's kind of look at that one. That would be example number 8. In example number 8, we're going to do the model, the population of Dallas using a logistic function. Okay, so in example number 8, it has the population at times t is going to be equal to this long drawn out thing. So that's what it looks like. Okay. So based on that data, so the T is year after 1900. So T is years after 1900. According to this model, when is the population 1 million? And again, on this one, so you would set this to 1 million, right? And you need to calculate this, okay? And again, you're not going to be able to calculate this. And you'll be able to calculate this in about 2 to 3 sections. But right now, you're not going to be able to do that. So you would just go ahead and plot this and find out where it meets the 1 million mark. Okay, so use it graphically, you would find it out. If you do that, you're going to find that T is going to be equal to 84.51. 84.51. So actually, you're going to add that to this because T is time after 1900. So the actual time in history when this happens would have been this. So it would be in 1984, right? About halfway through 1984. Okay? All right. We're good. And we are done with that section.